reduce parsing works, and also some of the nuances in predicting shifts versus reduces in a derivation. This video lecture talks about an algorithm that can help you predict shift and reduce actions called the LR2 algorithm. Before we can get into the specifics of how the LR2 parsing algorithm works, let's look at an overview of the concepts that we saw from the previous video lecture related to LR parsing. So we're going to start from the input string, from the terminal symbols, and we're going to search for a path to the start symbol. That's why it's bottom-up parsing. So we have shift reduce actions applied starting from the input string. And we apply shift and reduce, and we postpone decisions when possible or when necessary. So in some cases, you might want to postpone a shift and favor a reduce. In some cases, you might want to postpone a reduce in favor of a shift. So it depends on the situation which action would lead you to the start symbol at the end. And LR parsing, the name comes from these two letters L and R. L stands for left to right parsing. So we're going to take the input string and go from left to right, one token at a time. And R stands for the rightmost derivation, which is being constructed by the parser. And it's constructed in reverse or bottom up. So because we're starting from the terminal symbols, reaching the start symbol at the end. So if you look at this sequence of reduce operations, you can think of them in reverse as expansions starting from the rightmost non-terminal in each case. So we saw several examples of these before. We are going to study the LR2 algorithm in this lecture, and then when we look at some of the limitations of the LR2 algorithm, we're then going to extend it and get various extended versions of the LR parsing algorithm, namely SLR1, LR1, and so on, the concepts for which will become clearer when we have finished doing the LR2 parsing algorithm. The actions in shift reduce parsing involve some notation. So we know what to do when you shift and reduce. So far, we're quite familiar with this by now, but we are not yet familiar with the notation that we use to describe the parsing algorithm. So let's assume that I have a grammar, and this grammar has two rules. Two production rules, S goes to 0, S1, and S goes to 0, 1. Now, if I look at one step in a rightmost derivation, so I say rightmost, RM here stands for the fact that it's a rightmost derivation, which means I look for the rightmost non-terminal and expand it. So, and the star means that I can take 0 or more steps. So starting from S, I know that if I use rule number 1, so let's call this R1 and this R2. If I use rule 1 a couple of times, I can get to this state, right? I could get to 0, 0, S, 1, 1. Now in this case, if I take this S over here, which happens to be the rightmost non-terminal in that string because it's the only one in that string, and then I use rule 2 to expand it to 0, 1, you can see that that's one rightmost derivation step. Each of the shift or reduce actions are going to be essentially creating a stack in a state where I can apply a reduce action. So in this case, when I do a reduce, I'm going to be looking for the right-hand side of rule 2 here, and then replacing it with the left-hand side, which is the S. So in order to do this, we need some notation. So we're going to refer to the part before the right-hand side of the rule with alpha. In this case, is the first two zeros here. Then there is the right-hand side of the rule I'm going to recognize, which is 0, 1, which we'll call W. And then there is the part after that from the input string, which is the 1, 1, which we'll call beta. So alpha and beta are these Greek symbols that we'll use to represent arbitrary sequences of strings that it's handy to use this notation to talk about the algorithm. Let's continue with this example to get more familiar with the notation. So let's say that I want to then recognize this part, which is the right hand side of rule number 1, And one step of the rightmost derivation would be to recognize that 0s1 is the right-hand side of rule 1 and then replace it with the left-hand side, which is s. So in this case, if I look for alpha, w, and beta, alpha here would be the 0. W, which is matching the right-hand side, would be 0s1, and then beta is the context to the right, the string that's left over to the right, which is a 1. So now I would end up with, if I do this reduce, I would end up with 0s1, and you can see eventually if I want to reach, in one step I can reach the start symbol s by applying rule 1 again. You can see that alpha is the empty string, so alpha there's no alpha needed, so it's empty here, and so is beta. So the entire right-hand side is all that we have in this string, which we can replace with the left-hand side of rule 1 and replace it with the S, which is the start symbol. So with this notation, let's look at the actions in shift reduce parsing. Shift will add a terminal to the parse stack and advance the input. So whenever we do a shift, we're always going to push something onto the stack. Reduce, if alpha w is on the stack, so in this case, if I have alpha w 0, 0 and then 0, 1 on the stack, then what I would do is look for a rule which has w on the right hand side. As you can see, this rule has w on the right hand side, and replace it with the left hand side. So the first thing to do is to pop as many symbols as are in the right hand side. So in this case, there's 1, 2 symbols in the right hand side of that rule, rule 2. So I would pop 2 symbols, and then I would push something that represents either the left hand side itself or some state that represents the right hand side, the left hand side, onto the stack. So each reduce action involves popping 0 or more things from the stack, assuming that the rule that we are using is not deriving the empty string. There will be some symbols on the right hand side, and so we would pop some number of symbols equivalent to the length of the right hand side off the stack, and we also do a push. The push says we're going to replace what's on the stack with the left hand side of that rule. So this is called pruning the stack with the handle, or pruning the handle from the stack. So alpha w here is called a viable prefix because it tells us that the stack is in a situation which is amenable to a reduce action. If neither shift or reduce is possible, then we have an error and we should raise an appropriate error. That's another thing you could do because you can't either do a shift or a reduce. And finally, if you're done, if you reach the start state, or the start symbol rather, if you reach the start symbol and you've recognized the entire string, so there's nothing left in the input, then so as you can see in this case, there's nothing left after I've done the final reduce, then I can accept, which means that either now I have a completed parse tree or a completed derivation. Essentially, I'm done parsing and the string has been accepted, and it is a valid string according to this grammar. So there are some questions that arise. When exactly do we shift or reduce? So we've seen before, manually we could do this. We could sort of tell when to shift or reduce because we could look ahead and see if I do a shift now, I might not end up with a valid derivation, so I should probably reduce now. What the algorithm needs to figure out is what are the valid handles it needs and what is a viable prefix that appears on the stack, and then you can do a reduce. We need to deal with ambiguity. So when there is a shift reduce conflict, if it's a real one, then we need to specify this and tell the user who's asking the parser generator to generate the parser. They provide us with a grammar. We say, hey, your grammar is ambiguous. It has a conflict in it. So we need to be aware of which grammars work, which grammars don't work. And if you're reducing, we reduce always with a specific production rule, right? It's always reducing with either rule 1 or rule 2 or rule 3 whichever rule in the grammar you're using for the reduce. It's important to identify which one it is. And here again, you might have a case of ambiguity where you could reduce with two different production rules, in which case you have to report a conflict. Given a grammar and an input string and a stack, we know how we can use the stack to shift and then reduce. You perform these actions repeatedly in order to parse an input string. However, these shift and reduce actions were all sort of done manually. We were thinking about how to do them. Instead, what we're going to do now is entirely do this mechanically by looking at a lookup table, and the lookup table will tell us at every point, deterministically, it will tell us whether to shift or to reduce. And in fact, this approach is common across all of the LR parsing algorithms. So we are covering LR0 in this video lecture, but all of the LR parsing algorithms, even when you add additional look ahead, they're all table-based parsers. They all create a rightmost derivation in reverse, as we saw, going from the string up to the start symbol. One advantage of LR parsing is that they work with either type of recursive context-free grammar. As we'll see later, some other parsing algorithms don't deal that well with left recursive context-free grammars. So this is one advantage of using LR parsers. The data structures that LR parsing uses, again, this is common for all the LR parsing algorithms, but in this video lecture, we're going to focus on the LR0 parsing algorithm. The data structures that it uses is a stack. As we all know, we need a stack in order to do parsing for context-free grammars. It's a stack that will push states. So in a LR parsing algorithm, instead of pushing in the non-terminals directly, we're going to actually use a more abstract symbol, like a state. Just like we had states in NFA or DFA when we dealt with regular expressions. In a similar way for LR parsing, we're going to have these states. And what we're going to push and pop out of the stack are these states rather than the non-terminals or terminal symbols. We'll have an action table. So this is what I mean by a lookup table. The lookup table is going to tell us, given a state and an input. So this is very, very similar to the transition function that we had in finite state automata. A is some input symbol. You add a state S, and then you look at this input, and the action tells you what to do, either shift or reduce. In addition, because in the reduce action, if you remember, we have to pop symbols equivalent to the length of the right-hand side. So the popping is easy because we can say if I'm reducing with a certain rule, all I need to do is pop a bunch of symbols equivalent to the symbols that are in the right-hand side of that rule. But after that, we need to push a symbol as well, right? To start, assuming we've found the left-hand side, we need to continue parsing. And that's information is provided by this lookup table called the Goto table. The Goto table takes two things, a state as well, and it also takes a non-terminal symbol. So this is a non-terminal symbol on the left-hand side. So in both of these cases, the shift is easy. Every time you do a shift, you just push onto the stack. If I have x equals AB, let's say, and I'm doing a reduce with this rule R, then I'm going to pop two symbols out of the stack, and I'm going to push one symbol onto the stack, which corresponds to the left-hand side. The symbol, the state that I need to push is going to be read from this lookup table, the Goto table. It'll all become much clearer when you look at an example. So here's an example, action Goto table. So this part of the table with the symbols on top is the action table. This part over here is called the Goto table. And as you can see, it has a bunch of states. So it has state 0, 1, and so on. And here it has input symbols like the multiplication, open parenthesis, close parenthesis, ID. And $ is a special symbol which is going to signify the end of the input string. So $ means there's no more input left. It means you've finished shifting the entirety of the input into the stack, and if there's nothing left and we are at a certain state 2, you can see that there is the action which says accept. So if there's nothing left and you're on state 2 on the stack, then you can say, I've accepted the string. The string is generated by this grammar. Other actions, so all of these, this is for a specific grammar, this action Goto table. So the grammar that it's built for is shown here. It has 4 production rules. It has 2 rules with T on the left-hand side, which are 1 and 2 here. And it has 2 rules with F on the left-hand side, which is 3 and 4 here. S5 over here implies that if I'm in state 0 and the next symbol that's to be shifted onto the stack is open parenthesis, then what it does is a shift to state 5. So basically it pushes 5 onto the stack and then goes over to this row of this table here. So the next action it would do if it sees an open parenthesis again is shift to state 5 again. So it would push 5 onto the stack again. If I'm on state 5 and I see an ID, it shifts to state 8, right? So it goes over here. And if I'm at state 1, for example, then notice that the entire row here is a reduce action. So R stands for reduce, S stands for shift. The number after the shift is one of these numbers, the state numbers. The number after the R, or the reduce action, is a rule number. So they're totally different numbers. So that's one place that you could get confused. So be careful. Just in this notation, if I have S5, 5 is a state, right? This state over here. When I have R1, that 1 is this rule over here. The T goes to F rule, right? So it says reduce using rule 1. This part over here is the Goto table. It'll become clear when we go through a case of actually using this table to do parsing, but at a high level you can see that when I have recognized a rule, T goes to F, that means I replace F with the left hand side T. I'm going to look up the T here to see which state I need to go to next. So in this case, if I get to state 1 and I reduce using rule 1, I remove what's on the stack. I need to know what I need to push onto the stack, which corresponds to the left-hand side. So I go to the Goto table and I say, okay, I should push 2 onto the stack, and then I continue on from this state 2 over here. And so I would look up what to do next. So just in case the input is empty, I would accept the string if I'm at state 2. So these are the different notation that we use in order to specify when to shift, when to reduce. And when you reduce, what do you do about the left-hand side? That's the responsibility of the Goto table. I think the action and Goto table will become a lot clearer when we use an example and go through the steps in which we parse that input string and construct a derivation by doing these shift and reduce actions. So let's work through an example where we are using shift reduce parsing to parse this input. We're going to use the same table that I showed you in the previous slide. The grammar is, of course, the same. And what we want to do is construct a derivation or say that this string is accepted or not. So at this point, we know that all I need to do is remember all the reduce actions in order to build a parse tree. So if I have a sequence of shift and reduce actions that get me to this accept state, then I know that I can build a parse tree. So we won't actually build a parse tree. We just need to make sure that we have a sequence of shift and reduce actions. We know that looking at this grammar and looking at this input string, we can tell that this input string should be accepted by this grammar, right? So let's look at the sequence of actions would be and how we can use this table to do shift reduce parsing. What we're starting off with is this step here. 0 is the start state. So we always have a single start state. the start state is specified just like we specify the start state in a finite state automata. We are going to specify 0 here in this table. The state 0 is the start state. So we always push 0 onto the stack before we do anything. And then the entire input, this is the input, and you can see that the input is copied over here, and there is this extra symbol here which signifies the end of input. So dollar is used in order to match the end of the input so that we know when we should accept. And sometimes actually accept is not the only thing you can do. You might have shifted everything onto the stack, and as you've seen in previous examples, you might need to do a sequences of reduce before you can accept. So the dollar is quite useful because it specifies when you have run out of input to shift. So let's start with the start state 0, and the first input symbol is open parenthesis. So what I do is I look up 0 and open parenthesis, and you can see that the action that I've seen here is shift 5, which is the action that I will do. So all that shift 5 does is it pushes 5 onto the stack. And when I do that, I know that I've scanned the open parenthesis, so I move my input to the next token ID. I just look up in my table, so it's very mechanical. I look up 5 and I look up ID, and it says here to shift to 8, right? So that's what I'm going to do. I shift 8 onto the stack. Now when I go to state 8, notice that no matter what the input is, so this is why we call it LR. We call it LR0 because this is the look ahead for a reduce action. And as you can see, it doesn't matter what the next input symbol is. When you reach state 8, it's going to reduce. And it's going to reduce using rule number 3. Rule number 3 is F goes to ID. There's exactly one symbol on the right hand side of that rule. So we pop one symbol, which is 8. So 8 gets popped out. What's left on top of the stack is a 5. So we go to 5, go to state 5. We say, what is the left hand side of this rule? It's an F. So I look up the Goto table. So remember, the Goto table exists to tell me which state I should go to based on the left hand side of the rule. So if the left hand side of the rule can either be a T or an F, in this case the left hand side is an F, so I look up 5F and the answer is 1. I push 1 onto the stack. So as we know, a reduce action involves popping stuff from the stack equivalent to the length of the right hand side of the rule, and then pushing something for the left hand side of this rule. So in our case, we are not pushing the non-terminals directly, we are pushing these states. And we'll see why we're pushing the states when we actually construct the table. But for now, just use this table as a director, like it's directing you whether to shift or to reduce. Now let's go to state 1. In state 1 is another one of these states where you do a reduce. In this case, we're going to reduce using rule number 1. Rule number 1 is T goes to F. So we pop one symbol because the right hand side has one symbol. If we pop that one symbol, what we end up with is 5 again. This time, so now we're at state 5. So remember, we had popped out the 8, we popped out the 1. And now we are at state 5, and the left hand side is T. You can see that I need to push 6 onto the stack, which corresponds to the left hand side of rule number 1. So again, pop one symbol and push one symbol. Now we go to 6 and look at the input symbol close parenthesis, and we can see that it's shift 7. So shift to state 7. And that's what we shift onto the stack. The next input symbol is the multiplication operator. So we go to state 7. And now we can see that no matter what the next symbol is, it's always reducing using rule number 4. Now rule number 4, which is F goes to open parenthesis, T close parenthesis. You can see that there are 1, 2, 3 symbols on the right hand side. So what we're going to do is pop 3 symbols off the stack. So the top 3 symbols are 5, 6, and 7. We pop them out. We end up 0 is now on the top of the stack, and F is the left hand side of this rule. So we go and look up 0 and F. It says to push 1 onto the stack. So that's what we do. And now we have one multiplication. So the next step, which will go to the next page, so there's not enough room on this one. So same table, same grammar, and we have 1 on top of the stack and a multiplication operator. So that's 1. It doesn't matter what is in the input. It's a reduce action, and the reduce is going to reduce using rule number 1. We pop one symbol, which is the length of the right hand side here, and it exposes the 0. The left hand side is a t, so we look up 0 comma t, and it's 2, so we push 2 onto the stack. And then the input symbol is times, so we go to 2, multiplication, shift to 3, so we shift 3 onto the stack. The next input is id, so we go to 3 id, and it says shift to 8, so we shift 8 onto the stack. Notice that all of the input is gone. What we have next is $1, and when I'm at 8, I know that I need to do a reduce using rule number 3, right? Because all of these are reduce actions. And this one, you pop one symbol off the stack. So we pop this guy off. We go to 3 and look up f. So 3 and f will give me 4. So I push 4 onto the stack. When I go to state 4, it's reduce using rule 2. Rule 2 is t goes to t times f. And notice that I have 1, 2, 3 symbols. So I pop 3 symbols off the stack and I end up in state 0. So let me just clear the pen markings here. So I'm at state 0 and I have the left hand side of rule 2 is t. So I go to rule 2 state 2. When I'm in state 2 and the next input symbol is the end of input symbol, the $, I can accept, and that's my final action, is to accept the input string. Next, we're going to look at the algorithm to build the action goto table that we used in the example that we just saw. So once we have an action goto table, we know that it contains all the instructions for what to do. If I have a certain input string, at each step it tells me whether to shift or to reduce, etc. So this algorithm here, this algorithm is a parser generator. What it's going to do is generate essentially the action goto table. So this action goto table is then consulted by the shift reduce parser, which has access to a stack. This shift reduce parser will take input strings, produce parse trees or derivations. So this algorithm that we're going to look at next, when you produce an action goto table, can then be directly used by the shift reduce parser along with the stack to convert input strings into parses. A crucial aspect of this algorithm that we're going to look at, the LR0 table construction algorithm, is that when you're constructing this table that tells you when to shift or to reduce, you need to know that it's a valid step in a derivation. So it has to be a valid step in some rightmost derivation of that input string. So let's, for example, take this grammar that we've seen before, which has two rules, s goes to 0 s1 and s goes to 0 1. If I want to recognize that this 0 s1 should be replaced using a reduce action to the s symbol, which is the left hand side of this rule. So I want to match the right hand side, replace it with the left hand side. So this reduce action, so this reduce is valid only if, when I end up here to 0 s1, there should be another reduce, or it could be a shift, reduce, whatever. There should be a sequence of shift reduce actions that end up eventually getting to the start symbol. This reduce over here is only valid if you end up reaching the start symbol. So that's what we want, is we want it to be a valid reduce, and then we put it into the lookup table. We need a notion of a configuration set, and this configuration set is going to be used to represent the states that we saw. So if you remember, in our action goto table, we had those states 0, 1, 2, and so on. The action table had these symbols, input symbols on them. The non-terminals were, so this was the action part, this was the go-to part. So these state symbols are going to be created by computing what is called a configuration set. And I'll define it as follows. So we use a dotted rule. We're going to use this notion of a dot here in order to construct a dotted rule. So here the dot is before an F. So it's before this symbol F. And essentially it's used to predict all the rules with F as the left-hand side, so that it knows that at this point, when your dot is on this part of the right-hand side of the rule, it's all of the F production rules are valid expansions at this point. So I can take all of the F rules. So in this case, I have F goes to open parenthesis, T close parenthesis. And now I put a new dotted rule where the dot is on the extreme left of this rule, the right-hand side of that rule, right? So this creates a configuration set. It's also called an item set. So this is either called a dotted rule or an item. And if I have a set of these, so a set of items, it's called a configuration set. It's quite similar to the NFA to DFA subset construction, because we are essentially computing all of the different rules that could be predicted at this point in the input. Right? It's similar to what we did when we were simulating an NFA or doing the subset construction to construct a DFA. The closure property applies to this configuration set. And again, I'm going to define it formally now, and then we'll look at an example, and I think it'll become a lot clearer when we look at the example why we need to do this. The closure property is that if I have a dot before a non-terminal, so this is some right-hand side of an arbitrary context-free grammar rule, right? It's very generic. xi plus 1 is a non-terminal. Then if I have a rule where xi plus 1 can be expanded to its right-hand side is again some abstract set of symbols, y1 through ym. y1 or y, each of these could be either terminals or non-terminals, and there could be 0 or more of them. Then what I do in this closure property is just put that rule into the configuration set with the dot at the just before the first symbol. That symbol could be a terminal, could be a non-terminal, could even be the empty string. But the dot just appears to the left of that first symbol. And now you repeat this. So if y1 was itself a non-terminal, you would look up its rule. And let's say y1 goes through z1 through zk. And I would take that rule and I put a dot in front of the first symbol on the right-hand side of the y1. And that would again be added in. And it's computed as a fixed point. So what does a fixed point mean? It means that adding new rules. So I have this rule gets added to the set, and then I look at z1, and then I look at its right-hand side, and I add that to the set. At some point, if I can't add anything new to the set, I stop. At some point, because the grammar is finite, you might add the entire grammar into the set, or some subset of those production rules gets added to the set. So we keep doing this closure property over and over again to every element until no new elements get added. And that's what the fixed point property is. So again, it's going to be much clearer what this means when we go through an example, but it's good to know the notation as well. The starting configuration, we got to start from somewhere. We start from some set, and then we're going to do a closure on that set. We're going to always start with a new start symbol. The reason we do this is to have a unique start state. We always want a single start state, just like we wanted a single start state in a finite state automata. Here, we also want a single start state so that we know which start state to put on the stack to start off the process for parsing. And we create a new non-terminal called S prime. And then we add a new S prime production rule where S is the original start symbol. So let's say that you had multiple S rules. Let's take the concrete example that we've been using in previous slides. In this case, there are two rules with S on the left-hand side, and it's preferable to have one rule to be the start symbol to be a rule with only one rule. So we're going to add S prime goes to S, and now I can exactly have one rule here that guarantees me a unique start state when I'm constructing the lookup table. So the initial configuration set is going to be the closure of S prime goes to S with the dot just before the S. So if you remember, if I have the dot before the S here, the closure property says I should look up all of the rules that have S on the left-hand side and then put the dot. Put the dot just before the first symbol on the right-hand side. So the closure property is going to give us our starting state, essentially, for the lookup table, the action goto table. Let's look at example here. We have a grammar. I've added this rule. So T was the original start symbol. And what I've done is replaced T as the start symbol, and I've created a new rule called S prime goes to T, and that's going to be S prime is now our start symbol. There are two T rules, T goes to F and T goes to T times F, and F goes to ID, and then F goes to open parentheses T close parentheses. This should be a familiar grammar to you, because this is exactly the grammar that we used in the example to parse that input string before. When we worked through the action goto table, this was the same grammar. So let's start with the closure of S prime goes to dot before the T. So remember, the closure property says you look up all of the rules which have T as the left-hand side, right? So we start with S prime goes to dot T. We look up all of the rules with T on the left-hand side. So there's two of them, T goes to F and T goes to T times F. And we put the dot in front of that. So you put dot before T times F, dot before F. So we've added these two. Now the closure property says you should repeat this until you can't add any more. So you have to compute the so-called fixed point. So far we've predicted all of the rules for T, so we can sort of cross that out. And now the dot here is, there are two new cases. This dot is before a T, this dot is before an F. Well, the T we've already covered. So if we predict based on the T rules, we're just going to get this and this again. Since this is a set, we don't want to add the same symbol again. Like a set doesn't have any repetitions of the elements. But F we haven't done before. So we say, okay, we got to do F. You look up the rules. F goes to ID, F goes to open paren T close paren. And we add F goes to ID with a dot in front of the first symbol on the right hand side, and F goes to open paren T close paren. Again, the dot goes before the first symbol, and we're done with F. Now if you look at the F rules that we added, it doesn't have the dot before any non-terminal. They're both before terminal symbols. So we don't have any new symbols to add here, so we're all done. And the closure here is equal to this set of these dotted items, right? So notice that these elements of this set is not the context-free rules themselves, but the context-free rules plus a location for the dot, the dotted symbol. So each of these is a dotted item, and there are 1, 2, 3, 4, 5 elements in this set. And we're going to call this set I. It's being assigned to I. So I is a set containing these 5 dotted rules. The next concept is to take one of these configuration sets, find the successor for it. So if I have one of these configuration sets, so I have a set containing a bunch of dotted rules, then each of them have a dot somewhere on the right hand side. The next step is to compute the successor. So if there is a symbol to the right of the dot, so let's say that there is it's before an open parenthesis, or it's before an F, or it's before an ID. The next idea is to do something similar to what we did for the DFA. Figure out the successor state for this state. So informally, we want to move the dot over the symbol X. So wherever the dot is before some symbol X, we're going to move the dot over, and we remove all the other items that don't have So you only consider the items where the dot is before the X, and you don't consider any of the others. Okay, so this will become clear again when we do the example. And then the important thing is the third step, which is to compute the closure again. Okay, so this is fairly abstract. Let's look at a concrete example, and then the successor function will become much clearer. So this is the same set we computed before. This is the set for I. It has those 5 elements that we computed. Remember, we started off with S prime goes to dot T, and then we computed the closure of this, and we did it over and over again until we couldn't add any more to this set. And now let's compute the successor on this set based on the open parenthesis. Now if you look at each of these, this one doesn't have an open parenthesis. The dot is not before an open parenthesis. This one isn't. This one isn't. This one isn't. This last one is the only one that has a dot before the open parenthesis. So what we do is we take that element, we take any of them. So in this case, there's only one. There could be more than one. And what we do is move the dot across that symbol. So we're going to move it across the open parenthesis. So when we do that, so we move the dot over the open parenthesis. So I'll take the F, and notice this dot, I'm going to move it over. This dot before a T, and now I want to compute the closure. These parentheses are the inputs, and this parenthesis is a parenthesis for the function closure, right? Just to be clear. So when I compute the closure of this, I start with F goes to dot T. I predict all of the T rules, just like I did when I constructed I. I'm going to construct the closure on this dotted rule. T has 2 different rules. T goes to dot F, T goes to dot T times F. So I've done all of the T rules. So when the T is before this symbol, we've done it. We haven't done F yet, so we would predict F goes to dot ID, and F goes to dot open parenthesis T close parenthesis. So I've created this new set, which is this set is the result of doing successor on this input set on the symbol on the symbol open parenthesis. So what we end up with is a new set of dotted items. This should be the same. As you can see, F goes to dot T, so that's done. T goes to dot F, that's done. T goes to dot T times F, F goes to dot ID, and F goes to dot open parenthesis. So as you can see, the result of a successor function, it takes a set of dotted rules. So this set is the input. It takes a symbol. The symbol can be a terminal or a non-terminal. And the output is another set of states. It's possible that the output set of states is identical to the input set of states, just like it's possible for a DFA to have a transition back to itself. It's analogous to that. So far we know how to do a closure. We know how to do a successor. And that's really all the ingredients we need to build the action and go-to table. One interesting corner case for the successor function is if the dot is actually at the end of the right-hand side. So let's take an example. Let's say I have T goes to T times F, and at some point by repeated application of this successor function, the dot might end up on the extreme right of the right-hand side of this rule. Now if I ask for successor, I ask for successor on this set, which just contains this dotted item. Now it doesn't matter what next symbol that I ask for is. Let's just say I want it on open parenthesis. Notice that this dot is not before anything, and it's definitely not in front of open parenthesis. So in this case, I would just return nothing. So it would just be that this successor of this item set doesn't give you any output. So there's nothing to go to, no other set of states to go to, set of dotted items that you can transition to. So this successor on this input doesn't give you any new set of items. So far what we have seen is how you can augment a grammar with S prime goes to then the start symbol. And then we start with the closure over this rule S prime goes to dot T. That gives us our initial item. And then we do successor on this initial item on different symbols. So on all of the input symbols and all of the non-terminal symbols as well. So you could have any n union t as an input as the second argument to this function successor. Putting these functions together, what we get is this function items, and items is an initial closure based on this augmented start symbol. And then for each dotted item in this set C, I go through every possible symbol, either a non-terminal or terminal. And then I compute the successor of that set I and this symbol X. And then I add this to the set of this entire set of the set of items, right? So capital C is all the possible set of dotted items that you can compute. So if you start off with an initial set, which is the closure on the start, and then each successor will give you a new set of dotted items. Then we compute all the possible sets that you can compute until you can find no more, and that's when you stop. So when you've computed all the possible successor states, you stop. Again, this is very, very similar to the subset construction that we saw when you convert an NFA to a DFA. But let's look at a concrete example and put this all together. And I think it'll become a lot clearer to you as well when we look at an example. So we'll take an example grammar. So the grammar is the one that we've been using all along, right from the beginning when we looked at how we can use an action goto table. It's the same grammar. And as we mentioned, we will start with adding a new rule, S prime goes to T, because T is the start state. And we start with S prime goes to dot T and compute the closure over this dotted rule, which gives us this initial state. So we're going to call this state 0. We're just going to call this set of dotted items is our state 0. Notice it's the same as what we did before. The dot is before the T, so we predict all the T rules. The dot is before the F and the T. The T rules have been predicted already, so we predict all the F rules. Now we compute the successor. So let's compute the first successor on F. We look for all of the cases where F has a dot before it. So this is the only case in this, right? None of the others have a dot before an F. So this successor is giving me this transition on F. What I do is I move the dot across the F and then compute the closure. So if I move the dot across the F, I get T goes to F dot. And then I compute the closure over this. The closure over this, as we saw, the dot is on the extreme right, so it doesn't produce anything. There's nothing else that I can add. So this dotted rule is the only thing that I can put in this set. Is T goes to F with the dot at the end, right? The closure on this gives me nothing. And now let's look at a successor on T. Now let's look for a dot in front of the non-terminal T. And you can see here there's two places. There's this one and there's this one. So what we're going to do is move the dot across both of them. What we end up with is a set containing S prime goes to T dot, T goes to T dot times F. And now we have to compute the closure. The closure on this guy gives nothing. The closure on this also gives nothing because the dot is before a terminal symbol. So that's the state that I would get is just this set containing these two dotted rules. And that is a new, we haven't seen this set of states before. So we're going to give it a new number. So this was state 0, this one was 1, and this one is state 2. Let's start with a successor on state 2. We haven't quite finished with state 0. We'll come back to state 0 later, but let's do a successor function on state 2. So let's look at the dot so this transition is on the multiplication operator. So the dot is before the multiplication operator here. So what we would expect is T goes to T multiplication dot F. We look at all the F rules and we predict f goes to dot id, and f goes to dot open parenthesis t, and we repeat it until we get nothing new. So in this case, the dot is before a terminal, so that's doesn't generate any new dotted items. This dot is before open parenthesis, again doesn't generate anything new. So when we do a successor on multiplication, what we get is a new state 3, which we haven't seen before, which has these 3 dotted items. Next, let's look at state 3 and compute a successor on non-terminal f. So I'm doing this in an arbitrary order. It doesn't really matter which order you do it in. I'm just trying to create new states rather than just staying with the same old state as before. So you can do all of the transitions on state 0 first if you wish, and then do all of the transitions on state 1 and 2 and 3 and so on, all of this successors for each of the states one at a time. But that's kind of boring for the purposes of the video lecture, so I'm just going to try to generate new states, and that's why I'm starting with 3, and we're going to compute the successor on f. So let's look at where are the cases where the dot is before an f. We can see that this is the only case, so I would go t goes to t times f dot, and as we know from having done it before, like over here, that once you have a dot at the extreme right, the closure doesn't produce any new elements for you. So we do get a new state, a new set. This set contains just one dotted item, and that state we're going to call 4. Now let's go to state 3 again and compute the successor on the open parenthesis, dot before the open parenthesis over here. So what we can do here is to start off the closure, I would move the dot across the open parenthesis. I get a t, close parenthesis, t. So the dot is before the t, so I look up all the t productions and put the dot before them. The dot is before the f, so I predict all of the f. So now I have no more dotted rules that I can predict. So I get a state which comprises of these dotted rules. The next thing to check once you've generated this new set of dotted rules is to check whether you have generated it before. If you have generated it before, you shouldn't create a new state for it, right? Because you've seen it before. It should just have a transition back to that previous state. In this case, we haven't seen it before, so we assign it to a new state 5, and then we compute the next step, which is a successor on 5 on t. So t over here, there's a dot in front of a t over here, and there's nothing else. So there's only 2 of these. So if I move the dot across these, I would get f goes to open parenthesis t dot close parenthesis, and t goes to t dot times f. And that's a set I haven't seen before, so I generate a new state number 6, which has these 2 dotted items in it. So I'm not drawing the curly braces on these states, but they are each assumed to be a set. I'm not putting the curly braces just to keep things a little less cluttered. Okay, what the next step is going to be successor on the close parenthesis. So the dot here is best before a close parenthesis. And what we'll end up with is a dot at the end, and we compute the closure on this, and no new items come out, as we saw from previous cases like this one and this one, right? So we are now at a new state 7. Haven't seen that set of states before. Let's look at the successor on state 5 on ID. There's one dotted rule with the dot before the ID. So we move the dot across the ID and we get a new state, which is state 8. Let's look at the transition on the successor of state 3 on ID. So if I look at this, I can see that there's only one rule where the dot is before the ID. So if I move the dot across the ID, I would end up with f goes to ID dot. And if I take the closure of that, no new dotted items come out because the dot is right at the end. So notice that this is the first time we've generated a state that we've seen before, which is state 8. So in this case, I would just create a transition on ID from state 3 to state 8. I don't create a new state because I've seen this one before. Okay, so the next step is let's look at what is the similarity, what is the successor on 0 that would give me state 5. This dot, the initial closure here, was a successor on the open parenthesis. So let's compute the successor on the open parenthesis. There's only one rule with the open parenthesis here. And you'll see that it's going to be f goes to open parenthesis t, all of the t rules get predicted. This t goes to dot t times f gets predicted. And then because of this dotted rule, we predict f goes to dot id, and then f goes to dot open parenthesis t. Also notice it's a set, so the ordering doesn't matter at all, right? So if you look at this set and compare it to 5, you'll see that it's identical, right? So instead of, if I do a successor on open parenthesis from state 0, I will end up at state 5. It's the same set of states. So if the set of states is identical, like I said, to a previous state, then we don't create a new one. We just create a transition to that same state that was there before. Now let's consider a transition from state 5. So from this state, let's compute the successor on f. So if I was to compute a successor on f, what would that be? Well, let's look at all the cases where the dot is before the f. There seems to be only one case, which is here. That gives me t goes to f dot, and the closure on that gives me no new dotted items. And notice this is identical to state 1. So what I would do is a transition from 5 on the successor function on f gives me state 1. So I would draw a link between state 5 and state 1 and label the edge with f. I've added a transition from state 5 to state 1 on f. Now if I compute a successor on state 0 on id, I would move the dot across the id and I would end up with exactly what's in state 8. So I would create a transition starting from here and going through to state 8, and I would label it with id. So the successor on id from state 0 gives me state 8. Now let's consider a case where I'm at state 5 and I take a successor on the open parenthesis, which is something I haven't done yet from state 5, right? I've done successor on f and a successor on id, and that's about it. No, a successor on t as well, but I haven't done yet a successor on open parenthesis. So what I would do is look for a dot in front of an open parenthesis, which gives me that dotted rule, right? The dot just before the open parenthesis, and I compute the successor. So again, I'm just going to do it manually. So I would take the dot across the open parenthesis because I'm computing the successor on open parenthesis, right? And then the dot before the t, close parenthesis. I would predict all of the t rules. So t goes to dot f, t goes to dot t times f. I predict all the f rules. F goes to dot id, f goes to dot open parenthesis, t close parenthesis. And there's nothing else I can add. So that's the fixed point. There's no other dotted rules to add. If you look at it, it should look quite familiar, right? It's exactly the contents of state 5. So in fact, when I take a successor on open parenthesis, I end up having a loop back to itself on open parenthesis. So it's a self loop back to 5 if I see another open parenthesis. I can do this as many times as I want. It's similar to the star operator, if you remember in the finite state automata, because you can take as many open parentheses as you want. The contrast with a finite state automata is that in a context-free grammar, it's going to be able to match all the open parentheses with an equivalent closing parenthesis because of that rule. Has a closing for every opening, right? F goes to open bracket, T close bracket, ensures that for every open bracket there is a close bracket. So I've done here is added a self loop on the open parenthesis. So we're getting close to the end now. Let's go to state 6 and ask the question, what happens on a successor on the multiplication operator? What I would get is T goes to T multiplication dot f, f goes to dot id. So the dot is before the f, so I predict all of the f rules, and f goes to dot open parenthesis t, and there's no other dotted rules to predict because we've done all of them that are in front of a non-terminal. And notice that this is exactly state number 3. So what I would do instead of creating a whole new state is to create a transition here on the multiplication operator. Okay, so I've done that here. I've added a transition from 6 to 3 on the multiplication operator. Now let's check if everything is done, or do we have any other edges we need to add, or any new states that might come about because of a successor. Let's start with state 0 and look at every symbol where the dot is in front of it. So the dot is in front of T, and we've covered it. It's in front of F, and we've covered that. It's in front of ID, we've covered ID, and in front of open parenthesis, and we've covered that. Let's go to state 1. So we've covered state 0. We go to state 1. The dot is right at the end of that right hand side, so there's nothing to do for state 1. Let's go to state 2. The dot is in front of the multiplication, and this one doesn't count because it's right at the end. Nothing new can come there. So we're done with 2. Let's start with 3. 3 has a dot before the F, so that's covered. Before the ID, that's covered. Before the open parenthesis, that's covered. Let's go to 4. So 3 is done. 4, the dot is right at the end, nothing to be done. 5, there's dot before the T, which is done. Dot before the F, which is done. Dot before the ID, which is done. And then open parenthesis, done. So 5 is done. 6, the dot is before the close parenthesis, done. Before the multiplication, done. And 7, so 6 is done. 7 has dot right at the end of the right hand side, so that's done. And finally 8 has a dot right at the end, so 8 is done. So notice that there's no other successor functions to compute. We've created all the possible set of dotted items that we need to cover all of the outputs for all symbols, terminals and non-terminals. Now let's look at what this rule means. This rule says I'm the start symbol. S prime is my new start symbol. Once I have crossed over and recognize every possible derivation that can start from the start symbol S prime, that means that's the only way I can get the dot to the right at the edge of this right hand side. So when I'm in this state 2, it implies that I have predicted every rightmost derivation that starts from T in this automata, as you can see, that we have constructed. And so when I've done that, I'm ready to recognize the start symbol. That means that I can accept only if the input is empty. So I need to add that constraint. So this is the only constraint where you actually have to do one symbol of look ahead, is to make sure that the next symbol is the end of input. But if you look at all the other cases where the dot is right at the edge, over here, over here, over here, over here, each of those is a reduce action, and that can be done without looking at any symbol that appears at the next symbol. So T goes to F dot means I've accepted, I've recognized that entire rule. So I can say that when I reach state 1, I want to reduce using rule number 1, which is this one, the T goes to F rule. Similarly, at state 4, I can reduce using rule number 2, which is T times F. Notice that there is a path here. This is the T transition, this is the times transition, this is the F transition. That's why I got T times F. And for each of those T and F non-terminals, it's every possible rightmost derivation from those non-terminals. So everything has been computed in this. Everything has been computed in this automaton. The next one is state 8, which I'm going to reduce the F goes to ID rule. State 7, where I'm going to reduce using the rule number 4, F goes to open parenthesis, T close parenthesis. So again, if I am starting from an F, so I'm predicting an F over here, it's going to, there is a transition on an open parenthesis, a T, and a close parenthesis. And that's why I got to state 7. And that's how I can reduce using rule number 4. If you look at this automaton, so each of these consists of a transition from state 0 to state 1, or state 0 to state 2, state 0 to state 8, etc., I can take this finite state automata and represent it as a table. And whenever there's a transition on an input symbol, I put it in the action table. And whenever there's a transition on a non-terminal, I put it on the Goto table. So this is the action table. This is the Goto table. And notice that this table is exactly the table that we used in order to do the shift-reduce parsing before. Given this table, we know how to do shift-reduce parsing. I just look up at the table, do shifts and reduce, and manipulate the stack as needed. What I've shown you with this construction, all I'm doing is computing closures over these configuration sets, and then computing the successor function. As long as I can implement the successor function correctly, I can iterate that over and over again to get this finite state automata. And this finite state automata tells me exactly when to shift and which state to shift to. And it also tells me when I've reached a state when I've reached a state that I should reduce on, right? So when I reach state 1, I should reduce using rule 1. So it's everything I need in order to build a shift-reduce parser that is table-driven. If you look at this table that we've created from this finite state automata, you notice that it is a representation of the finite state automata, except that this part over here has to be, is not anything like a standard finite state automata because it has action that's on a non-terminal symbol. The other thing you can notice is that it requires a stack because it's giving you actions to do on the stack. So it's telling you at some point whether to shift or to reduce, and each of those are manipulations of the stack. The other thing is that every single element here, every entry only has one thing to do. If I end up with an entry that can either be a shift or a reduce, or I end up with two different, so if I end up here and I look at this and I say this could be reduce 1 or reduce 2, then I'm in a situation where this table has a conflict and I can't use it for parsing. So a conflict here would involve multiple clashes, basically two items trying to get into the same table entry, and that's obviously not allowed. So I can't have a parser with a lookup table where it gives me a conflicting advice, right? It has to say either shift or reduce. It can't say, I don't know, I guess reduce 1 and reduce 3, choose one. It can't do that because then it's not deterministic. The other thing you notice is that some of these entries are empty, and those are the cases which are errors. So if I'm on state 2 and I see an ID, it's a situation that should not arise. So if it does arise, it means that the ID is in a location which is not valid according to this grammar. So in any of these empty spots here, you would put some kind of error condition. So let's look at an example that has rules that can derive the empty string. So if you look at rule 3 and 4 in this grammar, A derives the empty string and B also derives the empty string. If you look at the language for this grammar, you can see that the start state here is an S. So we would, for the LR0 construction, add a new rule, which is S prime goes to S. And if I construct all the derivations that can start from S prime to get the language of this grammar, you can see that it's a fairly trivial grammar. It can either generate the string AB or the string BA. So it's a really, really simple trivial grammar, or so it seems. So let's do the set of items construction, the LR0 algorithm to construct the parsing table, the action Goto table. So we start with S prime goes to dot S. It predicts all of the S rules with the dot in front of it. So this and this. And then the dot is before the A. It predicts the A rule. There's only one A rule. And notice that since the dot before the empty string doesn't make any sense because it's the empty string. So when I predict a rule with the empty string, I directly predict it with the dot on the other side of the empty string. Essentially, we've recognized this rule already because it doesn't need any input to be reduced, right? So it can be reduced on the empty string. So that's why the dot is on the extreme right. And then this one predicts a B, which again is in a similar situation. Let's compute the successor on this. So the successor here can either be on an S or an A or a B. That's the only choices. This dot is right at the end, so there's no successor possible for them. So let's look at the transition on B. When I compute the successor on B, I move the dot across the B, and now the dots before the B, the terminal symbol B. So the only thing I can do here is compute the successor on the terminal B, which gives me the dot before the B. I compute the closure for that because the dot is before a non-terminal, and I end up with, again, the same thing that I did in the first state, which is B goes to epsilon dot. B is accepted or reduced without any input. Now there's a transition on the non-terminal B, which takes me to an item set that contains a dot before the A, which gives me transition on A. And now I'm right at the end. There's no more successors to be computed for that. Now let's do the same thing on transition on successor on A, sorry. Then we have the dot before the A. As you can see, it's very similar to the other sequence. Take a transition on A. The dot is before a non-terminal, so we predict all of the A rules, in which case there's only one, and the dot is at the end. Transition on the non-terminal A, then transition on B, and now we're at the end. The final transition or successor that we need to compute is on S, because the dot is before the S, and this is the accept state as we saw before, right? So this means if you reach this state, that means you can accept the string as long as the next symbol is the empty string. You notice that there are two reduce actions in this state. I can reduce A goes to epsilon with rule number 3, and I can reduce B goes to epsilon with rule number 4. So in this case, I can reduce with either rule 3 or rule 4. This state over here, I can reduce B goes to epsilon with the rule 4, and in this state over here, I can reduce using rule 3. So notice that over here, I have a reduce conflict. Here, there is no conflict. It just reduces and does a transition on this non-terminal B. So it pops 0 symbols on the stack and pushes a new state onto the stack, which is this state over here. That reduce action is also something which doesn't have a conflict. But notice that the table I generate does have serious problems because right from the first state, I don't know whether to reduce using rule 3 or 4. It's a conflict. Therefore, this grammar is not a LR0 grammar. Like I cannot construct a table, an unambiguous table for this grammar. Therefore, this grammar is not LR0. So there can be grammars for which when we do the table construction, we end up with a conflict. So let's take this example. It's a grammar that has similar things like multiplication and parenthesis. I've just added a new rule here, which is F goes to ID equals T. It's sort of like a variable assignment, when you have X equals 2 or something like that in a programming language. And when I compute these, so something that you should do is actually compute the closure from the start state and then compute the successor function on each of those states and compute this big finite state machine for this grammar. And when you do that, you'll see that you'll end up with a shift reduce conflict in one of the states. I can reduce using this rule, or I can shift on an equal to. So that's an example of a shift reduce conflict. That's going to happen when I try to compute the configuration set or set of items using this LR0 algorithm. I'm going to end up with this situation. I actually will also end up with the reduce conflict where F goes to ID and T goes to ID. These two rules will end up with the dot at the end in the same state. So unlike the example that I showed you earlier, for this grammar, we'll end up with a set of items where you end up with a shift reduce conflict. I mean, the numbers are arbitrary, so your number when you construct it will be different, but there will be some state which is set of dotted items where there is a shift-reduce conflict, and another state where there's going to be a reduce-reduce conflict. So in order to deal with these kinds of grammars, we need more look ahead to resolve these conflicts. So what we're going to do in the next video lecture is to look at a modification of LR0 where we're going to add some look ahead. And the look ahead will tell us which choice to take, whether to reduce this one or this one, whether to shift or to reduce. So it's going to resolve these conflicts by looking ahead one symbol.